Context is everything. Okay, so, I'm trying to invoke physics and everything else to get an idea here. Your x of t and y of t functions are positioned, right, on coordinate plane at this point, okay? Or in this context. If you think of t as time, the leading question that I tried to get invoking physics and everything else is, what can you calculate if you know x is a function of t and y is a function of t? Okay, well, you can use the Pythagorean theorem and approximate the displacement, but the thing you can calculate is the velocity, right? So we have the velocity function here, our purple velocity function. So we have v of t sub I star. Okay? And what's our expression for the velocity function? Either in terms of the cosine and sine functions or in terms of x of t and y of ti star.
You would take the derivatives of your parametric.
Yeah. So the derivative is, okay, well, another thing, we just want to find the distance here. We don't want to find the displacement. Okay? So really what we want to do is we want to find the magnitude of the velocity and multiply it by our t sub I, right? Okay? And that magnitude is just the square root of the components, the Pythagorean theorem applied to the components of the velocity vector, right? And that's what? That's x prime squared plus y prime squared. Okay? There's our velocity. Now, think of then delta SI as being the magnitude of V of Ti star times delta Ti, right? Okay? And that is just the square root of, now I wrote it more abbreviated up here because, consistent with my pattern, I didn't anticipate what I was going to draw, okay? And I didn't leave myself a whole lot of room, but I'm going to write it, the x prime squared plus y prime squared a little more specifically. It's x prime of Ti star squared plus y prime of Ti star squared times delta T sub I. Okay? So now we know what to fill in for delta SI. Depends on the derivatives, which give you the rate of change of position, right?